All right, here we go. Question 22 from our Precalculus homework number 13 in MyLab Math. It says use the principle of mathematical induction to show that the following statement is true for all natural numbers. So here we have a statement. It says 6 plus 12 plus 18 plus all the way to 6n can be represented by the formula 3n times n plus 1. So they're trying to make a statement here saying that you can find the sum of the first n multiples of 6 with this formula. Now, the first thing they want us to do, notice there are 7 parts, OMG. It says, what two conditions must the given statement satisfy to prove that it is true for all natural numbers? So let's go take a look at the scratch work and see what I've got for you. So here is the theorem for the principle of mathematical induction. It says the first condition is that the statement is true for the natural number 1. The statement has to be true for the first term of the series, and then condition number 2 that has to be met. If the statement is true for some natural number k, and it can be shown to be true for the next natural number, which would be k plus 1, if that condition is satisfied, then the statement is true for all natural numbers. So these are our two conditional statements. Let's go back to the MyLab Math and see if we can find these two. Okay, so the first statement, the statement is true for the natural number 1. That is the first statement for the theorem of mathematical induction. And then the statement is true for any two natural numbers k and k plus 1. I don't remember it being worded like that, so let's keep reading. If the statement is true for the natural number 1, it is also true for the next natural number 2. I know it didn't say that. If the statement is true for some natural number k, it is also true for the next natural number k plus 1. That's what the second condition said. So these are the two conditions that must be met. And then the next part showed that the first of these conditions is satisfied by evaluating the left and right side of the given statement for the first natural number. That means for when n is 1. Well, I got to tell you, the first box is freaking easy. That's just the first term of the series, so that's going to be 6. But then on the other side, we're going to have to evaluate this expression where n is 1 and work it out. So 3 times 1 is 3. 1 plus 1 is 2. 3 times 2 is 6. So it does satisfy the condition for when n is 1. And then next it says to show that the second condition is satisfied, write the given statement for k plus 1. So notice they have given me the sequence all the way up to plus 6k. So the next term of the sequence would be 6 times k plus 1. Recall that the next term of any sequence requires that k increments. So if you're at k, the next increment of k would be k plus 1. On the other side, now we're going to have to replace that expression. Every n gets to be k plus 1. So rewriting the expression 3n, but remember n now is k plus 1. So we're going to plug in k plus 1. It's got to be in parentheses. And then next, in the parentheses was n plus 1, but n is k plus 1. So that would be k plus 1 plus 1, which is actually plus 2. And checking that answer. Next part, part 4. If the statement for k plus 1 is true whenever blank, the given statement is true for all natural numbers. So if the statement for k plus 1 is true whenever, and I believe that's going to be whenever the statement holds true for some k, the given statement is true for all natural numbers. So again, this fits the second condition of our theorem. Okay, next part, use the statement for k. So here's our expression for when n is k to simplify the left-hand side. Yeah, so this is going to look a little confusing. Let me see if I can break this down for you. Notice that this first term of the expression looks like the formula we're trying to prove, 3k times k plus 1. So this would be the last term of the sequence for when n is k. So this first box is going to be 3k, k plus 1. That would represent the sum of the first k terms, and then I want to add the next term of the sequence. So the previous last term was 6k. So if I add one more term, that would be 6k plus 1. So again, what this shows, it shows the sum of the first k terms plus the very next term in the sequence should equal to the formula we just came up with for the sum of the k plus 1 terms of the sequence. And the next part, it says use the distributive rule and the associative rule to rewrite the right-hand side. So what they want me to do is take this expression, 3 times k plus 1 times k plus 2, and they want me to algebraically manipulate that into this form. So this is where the actual mathematics of the proof by induction comes in. So let's go to the scratch work and see how that works. All right, here we go. We've got the right-hand side of the previous step, and then this is where we're trying to get to. So what we're going to do here, what I'm going to illustrate first, notice the k plus 1 is a repeated factor. So I'm going to rewrite this expression as 3 times k plus 2 times k plus 1. All I did is switch the order of the two factors. And then what I'm going to do is I'm going to distribute the 3 into the first set of parentheses. Now that's going to give me 3k plus 6, but that is still multiplied by k plus 1. And then I'm going to take the first term of the first set of parentheses and multiply it by the second factor. In other words, I'm going to do the distributive property. So we're going to have 3k is going to be multiplied by k plus 1. And then we're going to do the plus 6. So that'll be 6 times k plus 1. And then notice we're at the destination we need to be at. We've got our k plus 1. So that coefficient is 3. We've got our k plus 1. That coefficient is 6. And back here at our MyLab math window, you're going to see basically what they wanted us to do is use algebraic manipulation to show that we do get the same expression as the left-hand side. So that's going to be 3k, k plus 1 plus 6 times k plus 1. Now, if you're wondering, can I just copy and paste this over? Yeah, but that doesn't prove that this is the same as this. That's what our work just showed, was that the expression on the right will calculate out to be the same as the expression on the left. And for part 7, the last part, use this result to draw a conclusion regarding the given statement. Now what we did is we just showed that the statement is true by mathematical induction. And so if we scroll down just enough to see everything here, which one of these statements is correct? Since the right side of the statement for k plus 1 simplifies to the left side of the statement for k, the second condition required to prove that the given statement is true for all natural numbers is satisfied, and the given statement is true for all natural numbers. That is not what mathematical induction says. That's not the theorem. Next, since the statement cannot be shown to be true for all values of k, the second condition required to prove the given statement is true for all natural numbers is not satisfied. That is false, because we did show that it is true for all natural numbers, so it was satisfied. Part C, since this statement is true for all values of k, the second condition required to prove that the given statement is true for all natural numbers is satisfied. The first condition for the principle of mathematical induction is also satisfied, so the given statement is true for all natural numbers. That is the correct statement. And that's going to do it for this problem. So if you have any questions or comments about anything covered in this video, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.